Welcome to lesson 37 in power system analysis. In this lesson, we will continue our discussion on power system stability. In the last few lessons, we were discussing rotor angle stability. We had discussed about the small signal stability. In the last lesson, we discussed about large signal stability, which we call as transient stability of power system. And there we introduced the concept of equal area criterion for trying to analyze the transient stability of a single machine connected to infinite bus bar system. In this lesson, we will continue with the same discussion, that is, we will start with the equal area criterion. We will look into different kinds of problems and how to solve or analyze the stability of power system under different conditions using the equal area criterion. We will take a few examples and then we will discuss this problem. We will start with the problem of effect of clearing time on stability. In fact, in the last lesson we talked about how the magnitude of a disturbance can affect the stability of the system. In this, we will talk about the how clearing time can affect the stability. That is, when a fault occurs in the system, in that case, if we clear the fault much faster, that is very quickly, then the system may remain stable, whereas if we take more time to clear the fault, then the disturbance, that is the accelerating power or decelerating power, will be remaining for a much longer period of time, and the system may become unstable under such situation. So, let us take a simple example where we have a synchronous machine connected to an infinite bus shown here through a transformer and a transmission line. P m is the mechanical input to the synchronous machine, that is turbine synchronous machine system, and we have a load which is connected here, and suppose we have a fault which occurs at this point P. Now, this point P is adjacent to this bus here. So, we can assume this fault to be almost same as to be on this bus. Now, what is going to happen when a 3-phase short circuit takes place? In fact, for most of the faults or most of the disturbance that we try to analyze for in transient stability analysis is the 3-phase fault, because it is the most severe fault on the system. Therefore, we will always be considering 3-phase fault here. In fact, the other faults like line to ground faults or double line to ground fault or line to line fault, all these are somewhat less severe than 3-phase fault, and therefore, if we want to analyze the stability of the system, we normally consider the most severe condition on the system, and if we find that the system is stable for this most severe disturbance, then we expect it to be stable for lesser disturbance. So, here we are considering a 3-phase fault at this point P which occurs, and if a 3-phase fault occurs at this point P, which is same as this point or this bus bar. So, the voltage at the bus bar is going to go down to 0, which means that the power flow, electrical power output from the generator to the infinite bus will drop down to 0. That is, the electrical power output from this synchronous machine will be 0, because here the voltage is 0, and this is a purely reactive circuit. We have a transformer, we have the transient reactance of the machine, and this is a fault, 3-phase fault here. So, the current which is flowing in this into this fault will be a purely reactive current, and there will be no real power which will be coming out from the machine. So, the real power output from the machine during the period of the fault is going to be 0. Now, if we clear this fault by opening the circuit breaker here, then the system will again be restored. So, that means once we open this circuit breaker, the fault will get isolated. This function is done by means of relays, which will sense this short circuit current flowing through this part of the circuit and will give a command to the circuit breaker to open, and once the circuit breaker opens, this fault is isolated from the system and the voltage at this bus will recover back to its normal value, and there is going to be a power transfer from the machine to the infinite bus of the system. So, let us see how we can analyze this situation by means of equal area criterion. Okay, so, let us assume initially the system is working at this point P m, that is the mechanical input to the system is P m and the electrical output also is equal to P m, that is P E is equal to P m just before the fault has occurred, and the operating point of the system is at this point A. The power angle of the machine under this situation is delta 0. Now, once the fault occurs on the system, that is when it is operating at this point A, the speed of the synchronous machine is synchronous speed. The system is working under normal conditions with power angle delta 0. Now, once this fault occurs, what happens is the electrical power output goes to 0, that is the electrical characteristics, if you see, shifts from point A to point B here, that is the electrical power output becomes 0, and what we have instantaneously is a large amount of accelerating power, that is accelerating power which is equal to P m, because P m minus P e is the accelerating power and P e is equal to 0 in this case. So, the accelerating power available in this time is P m. Here, because of this large amount of accelerating power, there is going to be acceleration of the rotor, and therefore, delta angle will start increasing, but the electrical power output will remain 0 because the voltage at that bus is 0 and only reactive power is flowing. So, real power output from the generator will be 0 and the characteristics or the operating point will start moving on this x axis like this. So, it will keep moving like this, that is delta angle will keep on increasing like this, and once it comes to say point C, where we clear this fault by operating the or opening the circuit breaker as shown here, that is this circuit breaker we open. So, the fault gets cleared. Now, if the fault gets cleared once we reach this angle delta C, which we will call the clearing angle, then what happens? The electrical power output now will suddenly jump from C to D, because with angle delta C, the electrical power output, which is P m or P max sin delta. Now, delta is equal to delta C. So, it is P max sin delta C, and the value for this is coming up to this point D. That is, the operating point now suddenly shifts from point C to point D once the circuit breaker is opened. Now, what is happening? Now, we have electrical power output which is much larger than the mechanical input, and so there is going to be decelerating power available, that is P m minus P e is negative. So, the rotor will start decelerating. However, when it started from this point and reached to this point, the speed has also increased, that is speed is now supersynchronous. So, at this point the speed is supersynchronous and the delta angle will keep increasing, though the rate of increase is going to be much lower, because now we have deceleration acting on the system. So, the speed of the rotor will start slowing down, but still it will be above the synchronous speed. Now, suppose when it reaches this point E, the speed has become equal to the synchronous speed, then what is going to happen? Now, at this point we have so much of electrical power output available and the mechanical input is only this much. So, this much amount of decelerating power is available. So, now the speed is going to go down, and as speed goes down, delta angle will also reduce, because we are measuring delta as with respect to synchronously rotating reference frame. So, speed is going below synchronous speed. So, delta angle will show a reduction. So, delta will keep on reducing like this. When it reaches this point A, we will find that P m is equal to P e, but the speed is lower than the synchronous speed, and therefore, the delta angle will keep on reducing, and we will find that as it reduces, we have accelerating power available. So, speed will try to increase, and we will get some point where we will again get the speed coming back to the synchronous speed, but since during that time we have accelerating power available. So, again we will have an oscillation taking place, and because of damping available, these oscillations will die out, and finally, the system will come back to an operating state, which will be the same point, operating point A. So, this is what the situation takes place. Now, as we have seen while we discuss the equal area criterion, so that the area under acceleration must be equal to the area under deceleration. So, this the area under acceleration is given by this rectangle A 1, that is from A the operating point shifts to B. This is the amount of accelerating power available, and this power remains constant up to point C, where the circuit breaker opens to clear the fault. So, the accelerating power is given by A 1. Once the fault is cleared, the operating point comes to D and it moves from D to E along this curve. So, decelerating and P m all the time, we have assumed it to remain constant. So, P m remains here. So, decelerating power available at different time will be like this. So, the total decelerating area available will be given by this A 2. So, what we find is this point delta 2 will be reached when A 1 is equal to A 2, that is accelerating area is equal to decelerating area. So, we will use this criterion to find out the angle delta 2 or delta c. Now, there is a question which comes is, now suppose we do not open the circuit breaker at this point delta c, but we allow it to move further, that is the action of the relay and circuit breaker takes longer time. Then what happens? This point C will be shifting further on this side, which means the accelerating area will be becoming larger and larger, and if that happens, then we will find that what is the maximum decelerating area which we can get will be up to this point only, that is above this line, and up to this point is what we will get as decelerating area. And if we find that if delta 2 can be shifted maximum up to this point, that is this angle at this point only, if the movement goes beyond this, that is delta 2 goes beyond this angle, then we again have accelerating power available. So, accelerating area is further going to increase. That means, we say that we will get a limiting condition when we have this delta 2 equal to this point, that is this delta 2 will be equal at this point, which is same as pi minus delta 0, because here we have delta 0 and here we have pi. So, this angle will be pi minus delta 0. So, till pi minus delta 0 is the maximum angle which delta 2 can take. If it delta 2 goes beyond that, then the system becomes unstable, because in that case the accelerating area is going to become more than the decelerating area, because the maximum decelerating area can be available only up to this point. The same case is shown in this figure. That is, what we have done is we have allowed, or we have taken more time for the circuit breaker to open, that is fault to be cleared. So, if we clear this fault around this point, that is delta clearing time is this, then we will get the decelerating area up maximum up to this point, and if this A 1 is equal to A 2, then we have a limiting condition for transient stability, that is the delta 2 is now equal to the maximum delta which is possible under this situation, and therefore, this is a limiting situation, and we call this angle for clearing the fault as critical clearing angle, because if we have the fault clearing after this critical clearing angle, then the system becomes unstable and we must clear the fault before this delta CR for the system to remain stable. So, this is what we see, that this is how we are seeing that fault clearing time or the fault clearing angle is affecting the stability. That is, if we make our clearing angle greater than delta CR, then the system becomes unstable. If we make it less than delta CR, then system will remain stable, and at delta CR we have limiting stability, that is, it is just stable at that condition. So, now we need to find out what is this critical clearing angle for this system. So, let us say from this system we have seen this delta max is equal to pi is angle here and this is delta max. So, this angle is equal to delta 0. So, delta max is equal to pi minus delta 0. So, delta max is pi minus delta 0. P m we know is the mechanical input and initial operating point before the fault. The system is having P m equal to P e, which is same as P max sin delta, where P max is E v by x. So, we have this P m is equal to P max sin delta 0. Therefore, the area A 1, accelerating area A 1, if we look at this area A 1 will be equal to how much? P m minus P e is 0 in this case. So, P m into delta C r minus delta 0. So, this is P m minus P e, which is 0. So, integral from delta 0 to delta C r P m minus P e d delta, that is what we have as the accelerating area, and this in this case comes out to be, since P e is equal to 0, this comes out to be P m delta C r minus delta 0, because P m is a constant, it is not a function of delta. So, we get accelerating area which is a rectangle in this case, which is P m into delta C r minus delta 0. Mind it, when we are doing this, we must use these delta angles in radians. Otherwise, if you use them in degrees, there will be problem. P m is in per unit, delta values will be in radians. Now, what is the decelerating area available? this will be from delta CR to delta max integral P max sin delta, which is the electrical power output. That is, if we see here, this is P max sin delta from delta CR to delta max. So, this is this curve that we have, sorry, this is this curve that we have minus P m. So, this area is integral from delta CR to delta max minus P m d delta. So, this is what we have got, A 2 is equal to integral from delta CR to delta max P max sin delta, which is the electrical power angle characteristics, minus P m d delta. This is equal to P max cos delta r delta CR minus cos delta max minus P m delta max minus delta CR. So, we have just integrated this, sin delta will become cos delta and so on. So, and putting the limit delta max and delta CR, we will get this relationship. Here we have got cos delta CR minus cos delta max, because the integral of sin delta will be minus cos delta. So, here we have got P max cos delta CR minus cos delta max minus P m delta max minus delta CR. For the system to be stable, A 2 must be equal to A 1, that is, the decelerating area must be equal to accelerating area, and from these two relationships, that is using the relationship A 1 is equal to, that is this is equal to this, we can simplify and finally get cos delta CR is equal to P m by P max delta max minus delta 0 plus cos delta max. Now, the value of delta max is known, because delta 0 is known and P m is known and P max is also known from the system. Therefore, we can calculate delta CR. So, delta CR, as I said earlier, we call this as critical clearing angle, because if we clear the fault with when the delta angle has not reached delta CR, then the system will be stable. If we clear the fault after the delta CR angle, that is when the rotor has exceeded delta CR, then the system becomes unstable, and this is what we have written. Once you have cos delta CR, you can find out delta CR. So, this is how we find out the critical clearing angle. Now, in this case, since P m remains constant during the time of the fault, the accelerating power is remaining constant. Therefore, we for this kind of a situation, we can also find out the critical clearing time. So, because we need to find out critical clearing time, that is, what is the time in which we must clear this fault. So, we have the swing equation, d 2 delta by d t 2 is equal to pi f by h into P m minus P e. P e is equal to 0 for the fault condition. So, we are writing this equation for the faulted condition, that is when the fault is on. So, this is the condition, we integrate it twice, then we will get delta, which is a function of time, is equal to pi f by 2 h P m t square plus delta 0. This is valid for t up to the, that is clearing time. Up to the clearing time, this is going to be valid. So, I should not write this as critical clearing time, but up to the clearing time. So, delta is given by this, and therefore, since delta CR will be equal to pi f by 2 h P m T CR square plus delta 0. So, that is what we have done is, here we have substituted for T CR, that is the clearing time. So, at the clearing time, the critical and clearing angle is given by this relationship. So, delta CR is equal to pi f by 2 h P m into T CR square plus delta 0, and since we know delta CR, therefore, we can calculate the critical clearing time from this relationship. So, let us take an example to work this out. So, from this relationship we can calculate TCR, which we have written here like this: TCR is equal to square root of 2 h into delta CR minus delta 0 by pi f into P m. That is simply finding out this, we take on this side. So, delta CR minus delta 0, and this whole term which is a constant can be taken on this side. So, this is 2 h by pi f into P m, and this is equal to TCR square. So, taking the square root, we will get TCR is equal to square root of 2 h delta CR minus delta 0 by pi f into P m. Now, let us take an example to see how this works. So, for the system shown, both the terminal voltage and infinite bus voltage are 1 per unit. So, for this system, the voltage of this the terminal voltage here and the infinite bus voltage, the terminal voltage of the generator here and the infinite bus voltage are 1 per unit, and the generator is delivering 1 per unit power. So, 1 per unit power is flowing from this generator up to the infinite bus. Calculate the critical clearing angle and the critical clearing time when the system is subjected to a 3-phase fault at point P on the short transmission line. That is, at this point, that is again same as this point, which is this fault here is similar to a fault on this bus, because the voltage drop here is going to be extremely small. So, this voltage here when the fault occurs is 0. So, the voltage at the bus will also be 0. Fault point P on the short transmission line, H is equal to 5 megajoules per MVA. The reactance for the transmission line is shown here. The transient direct axis transient reactance for the synchronous machine is given as 0.15, and for the transformer it is 0.1 per unit. All the values are on the same base. Now, what we have to do is, when we need to find out the power transfer relationship between this machine to the infinite bus, we need to find out the internal voltage of the synchronous machine. So, first thing we need to do is find out the internal voltage of the synchronous machine, because what we have been given is the machine terminal voltage is 1 per unit. Now, from the terminal of the machine up to the infinite bus, what is the reactance of the systems? The series reactance between the terminal voltage and the infinite bus is coming from this transformer and these two lines in parallel. So, it is j 0.1 plus j 0.5 by 2. So, this comes out to be j 0.35 per unit. Now, generator is delivering 1 per unit power. So, we know that P e is equal to V t into V by x into sin delta, where V t is the terminal voltage of the machine, V is the infinite bus voltage, x is the transfer reactance, that is reactance between the terminal of the generator up to the infinite bus. So, V t V by x into sin delta, V t is 1, V is also 1, and the transfer reactance is 0.35 as we have calculated just right now. This, so 1 into 1 by 0.35 sin delta, which gives that sin delta is 0.35 or delta is equal to sin inverse 0.35 or 20.49 degrees. That is the initial operating point. We have the terminal voltage with an angle of with a magnitude of 1 and angle 20.49. So, terminal voltage we have got like this. Now, we can calculate, once we know this voltage and the voltage of the infinite bus, we can calculate the current, which will be simply V t minus V divided by the reactance of the system. So, V t which is, we are saying this is angle delta, we have written here delta 2. So, 0 angle delta 2 minus 1.0 angle 0 degree, this is V. We have chosen, as we have said earlier, we always choose the reference angle, which is the angle for the infinite bus. So, voltage at infinite bus is having the reference angle 0. So, 1 angle delta 2 minus 1 angle 0 divided by j 0.35, this comes out to be 1.016 with an angle 10.2 degrees. So, now we know the current and we know the impedance of the system. The transient internal voltage, that is, we are trying to find out the voltage behind the reactance, is equal to, then this is the voltage this is the terminal voltage. So, terminal voltage plus the drop in the transient reactance of the machine. So, terminal voltage plus the drop, the reactance is j 0.15 and the current is 1 plus j 0.18, that is what we had seen here, 1 plus j 0.18. So, using this we will get the voltage behind the transient reactance as 1.038 angle 28.786 per unit, that is delta 0 we have got as 28.786 degrees. Now, the series reactance between the transient internal voltage and infinite bus, that is between E dash and infinite bus, is equal to how much? This is 0.15, which is the transient reactance of the machine, plus 0.1, which is the transformer reactance, plus 0.5 parallel 2 lines. So, 0.5 by 2. So, this is what we have got here. Total transfer reactance is 0.15 plus j 0.1 plus j 0.5 by 2. This comes out to be 0.5. So, the power angle equation for the machine now can be written as E V by x into sin delta. This is equal to 2.076 sin delta. Now, the initial rotor angle, as we have seen, is the angle of E dash, which is coming out 28.760. This we can find out from this relationship also, that is P E initially is equal to 1 per unit. So, putting this 1 per unit is equal to 2.076 sin delta. From there also we will get the same value, that is delta 0 initial operating point power angle is 28.786 degrees. Now, we can calculate the accelerating area, which will be from delta 0 to delta C r P m d delta, because P E in this case is equal to 0. When the fault has occurred at this point, then the power transfer from this will be 0, because the voltage at this bus will be 0, and all the circuit only has reactance. So, the current short circuit current will be purely reactive, no active power will be flowing in this case. So, we have accelerating area given by P m delta C r minus delta 0, as we have seen in the previous case, that is here we had seen this is P m delta C r minus delta 0. So, same thing we are writing in this case also. So, this comes out to be P m delta C r minus delta 0. A 2 will be from delta C r to delta max, P max sin delta, that is P minus P m d delta, and this is equal to P max cos delta C r minus cos delta max minus P m delta max minus delta C r, where these are in radians. Equating A 1 and A 2, we will get delta C r is equal to P m by P max into delta max minus delta 0 plus cos delta max. So, this is the relationship that we get for calculating the critical clearing angle. So, now delta max, as we have seen, is equal to pi minus delta 0 and P m is equal to P max sin delta 0. So, substituting for delta max and P m, we will get delta CR is equal to cos inverse pi minus 2 delta 0 sin delta 0 minus cos delta 0. Substituting the value of delta 0 in this relationship, we will get this as cos inverse pi minus 2 into 0.5024 sin 28.786. Here, as we said, whenever we are using delta 0, we are writing the value not in degrees, but in radians. So, 2 into delta 0 in radians, that is 28.786 in radians, that is 28.786 into pi by 180. So, this is equal to this sin this much minus cos this much. This, when we solve, we get this as 1.4176 electrical radians, which we can convert into angles if we want. Now, if the time to clear the fault is denoted by T c, then for the time t less than T c, we have this relationship, that is less than equal to T c, that is till the fault is on. We have the relationship d 2 delta by d t 2 is equal to omega s, that is twice pi f by 2 h p m, as p is equal to 0. Now, from this we will integrating once, we will get d delta by dt is 0 to t omega s, this is not w s, omega s by 2 h p m dt. This is equal to omega s by 2 h p m plus t plus d delta by dt at t 0, which is the initial operating point, and since the change in speed does not take place instantaneously. So, d delta by dt at t is equal to 0 plus is 0. Therefore, we have here no term for integrating in constant of integration, that is constant of integration in this case is 0. Again integrating again, we will get omega s p m by 4 h t square plus delta 0, the same relation that we had shown earlier, and in this delta t at t is equal to the clearing time is equal to omega s p m by 4 h t square, that t at critical square plus delta 0, t c r square plus delta 0. From this we can get delta c r is this much, and since we know the value of delta c r, so we can calculate t c r in that term. So, this comes out to be 4 h delta c r minus delta 0 by omega s into p m. Substituting the value, t c r is equal to 4 into 5 is h is 5 megajoules per MVA. Delta c r is 1.4176 as we have calculated earlier. Delta 0 is 0.5024 radians as we have calculated earlier, divided by omega s, which is twice pi f. So, this f is 50. So, 314 into p m, p m value is 1, that is initially the machine is supplying 1 per unit power. So, we get the critical clearing time as 0.241 seconds. So, this is how we can calculate the critical clearing angle as well as critical clearing time for a system where the fault, when the fault occurs, the electrical power output becomes 0 during the faulted condition. Now, let us take another condition. We have a system where we have synchronous machine providing power to the infinite bus by means of parallel transmission lines. Now, if we lose one of the transmission lines, what is going to happen? So, let us see this condition. So, sudden loss of one of the parallel lines. Now, the electrical power output P e is equal to E dash V by x d plus x 1 and x 2 in parallel, that is the two transmission lines, the reactances we have as x 1 and x 2. So, normally these will be same. So, we have this x 1 and x 2 in parallel. So, E dash V by x d plus x 1 and x 2 in parallel into sine delta. This is we call as P maximum sine delta. Immediately on switching off the line 2 power angle curve, that is, if we switch off one of the line suddenly, then what happens? The reactance now in this case, when one of the line goes off, say line 2 goes off, this is x 1 and this is x 2. Now, the line 2 goes off, that is, this line is open. So, the transfer reactance now will be the x d reactance for the synchronous machine plus x 1 the reactance of the transmission line. So, the transfer reactance from the synchronous machine up to the infinite bus is now x d dash plus x t. So, this is what we have seen here. So, in the electrical power output under when the line one line is switched off, we are writing it as P E 2 is equal to E dash V divided by x d dash plus x 1 into sine delta, which we write as P max 2 sine delta. So, this when both the lines are working, we have P max 1 sine delta as providing us the electrical power output characteristics or the electrical power angle characteristics for the machine with two lines, both the lines on, and this is providing us the electrical power angle characteristics when one of the line is switched off, that is when line 2 is switched off. So, if we see this condition, that is this line is switched off, then now what we are finding from here is we have two different power angle characteristics for two different operating condition, one when both lines are on, another when one line is off. Okay, so, for a case where we have a synchronous machine supplying power to infinite bus bar through two parallel transmission lines, we have the electrical power characteristics under when both the lines are operating given by this relationship P 1 is equal to P max 1 sine delta, where P max 1 is equal to E dash V divided by x d dash plus x 1 and x 2 in parallel, as we can see from this figure, where we have x 1 and x 2 the two transmission line reactances, V is the infinite bus bar voltage and its angle is taken as reference, x d dash is the transient direct axis transient reactance of the synchronous machine, E dash is the voltage behind the transient reactance for the synchronous machine, and delta is the power angle, that is the angle by which the voltage behind transient reactance leads the infinite bus voltage, and P m is the mechanical power input to the turbine generator system. When one of the line is suddenly switched off, which may occur because of we want to take this line out for maintenance, or maybe a maloperation of one of the circuit breakers due to some reason, then in that case the transfer reactance will change from x d dash and x 1 x 2 in parallel to x d dash and x 1 in series, because this is now switched off. So, in this case the electrical power output characteristics will be given by P E 2, which will be P max 2 sine delta, where P max 2 is given by E dash V by x d dash and x 1 in series. So, this is these two characteristics on P delta plane can be shown here, where this characteristics is for the both lines on, and the other characteristics P E 2 is with line 2 all out from service, only line 1 in service. Now, P m is the mechanical input to the system. Under steady state, the electrical output P E will be equal to P m, because we are considering this system to be a lossless system. So, the operating point will be given by this point A, and the angle delta will be equal to delta 0. This will be the operating point where P m and the characteristics of the electrical power output intersect. Now, when the line 2 is suddenly switched off, then the transfer reactance will immediately change to x d dash plus x 1, that is much larger value, and the electrical power output characteristics will shift from this characteristics to the other characteristics. Since delta angle cannot change suddenly, so the point will shift from A to this point B, where delta angle will be equal to delta 0. Now, we have A B amount of accelerating power available, which will make the rotor turbine generator rotor system to accelerate. Since we are measuring this angle delta with respect to a synchronously rotating reference frame. So, because of the acceleration of the rotor, delta angle will increase. When it reaches this point C, then we have the electrical power output increased and up, and it will become equal to P m. But since the rotor has accelerated all through this period, the speed of the rotor will be higher than the synchronous speed. So, still rotor angle will keep on increasing, but once it crosses point C on this characteristics, the electrical power output now is more than the mechanical input. So, rotor will start decelerating, and so speed will start decreasing from a supersynchronous speed, and till say it reaches this point D, where it becomes just equal to the synchronous speed. Now, this point D can be found out by equating these areas A 1 and A 2, where A 1 is A B C and A 2 is C D E. A 1 is the area during which the rotor is accelerating, whereas C D E is the area during which rotor is decelerating. This is what we get from the equal area criterion. So, once it reaches point D, what happens is we have so much of decelerating power available, and the speed is synchronous speed. So, rotor will start its speed will start going below synchronous speed, and so delta angle will start decreasing. Again it will come to C, where there will be neither acceleration nor deceleration, but since the speed will be lower than the synchronous speed at this point, delta will keep on decreasing till it reaches point B, where it will again attain synchronous speed, because during this period it will start accelerating. And so, we will see that the rotor will oscillate between these 2 points B and D on this characteristic. However, since the system will have some damping available, this oscillations will slowly decrease and will get finally damped to, and will come to a steady state operation at this point C, which will be the new operating point, and the angle will be given by delta 1. The maximum angle which this rotor will attain will be given by this point D, which is delta 2, and this we obtain when A 1 is equal to A 2. So, now again if we want to find out the critical clearing angle for this case, then we can do that, because in this case again critical clearing angle will come when we have the maximum angle, which is when the operation comes to this point D, and this point if you see will be having an angle which will be equal to pi minus delta 1. So, delta max in this case is pi minus delta C or delta 1, whatever we write. Here we are writing this as delta 1. So, what we will say is this is point delta 1, which is the operating point, and the maximum which we can reach will be this point, that is this point, which will be equal to pi minus delta 1, that is the point where P m cuts this characteristic, second characteristics, that is characteristics when line 2 is out. Now, let us take another case when a short circuit at one end of the line takes place. So, instead of now removing one of the lines, we have now a short circuit taking place at one end of the line, either this end or this end of the line. In either case, what happens is the fault is on either this bus. If the fault occurs here, the fault is same as it is on this bus. If the fault occurs here, it is same as on this bus. In both these cases, the voltage at this bus or this bus becomes 0, and therefore, there will be no power transfer taking place between the synchronous machine and the infinite bus under this condition. So, during fault condition, that is when a 3-phase fault occurs at either end of the line, during the fault period there will be no power transfer taking place between the synchronous machine and the infinite bus. That is, we have taken the fault on this end of the line, this end of the line. So, what we have is this end of the line is shorted, which is same as this end of the line is also shorted, it is grounded. So, we have the power, no power transfer feasible under this condition, because a 3-phase fault has occurred. So, this bus voltage has come down to 0. So, in this case, the power angle characteristics before the fault is E dash V by x d dash with x 1 and x 2 in parallel into sin delta, that is P max 1 sin delta. And in the second case, when the fault is there, the power transfer, electrical power output is 0. So, P E 2 is equal to 0. Now, if the fault is cleared by opening both these circuit breakers, so the fault, once the fault on the line is cleared by opening both these circuit breakers, the system will recover, but now the transfer reactance will be x d dash plus x 1 only in this case. So, we have the post fault condition when the line, one of the line is tripped, the faulted line is tripped, then we have P E 3 is equal to E dash V by x d dash plus x 1 sin delta, because now the transfer reactance is x d dash plus x 1, only one of the line is now tripped. So, this is equal to P max 3 by sin P max 3 sin delta, or in this case I am sorry, this is written as P max 2, which it should read P max 3. So, what we have is system is initially operating at this point where P m is equal to P e. The fault occurs, the electrical power output goes down to 0. There is this much amount of accelerating power available, and therefore, delta angle keeps on increasing. So, during fault, the delta angle profile will be like this. So, delta angle will keep moving along this line. Now, suppose at this point, when delta angle has reached delta c, we clear the fault. What will happen? We have cleared the fault by opening line 2. So, what is going to happen? This electrical power output will jump now to this point, and from this point it will now be moving on this characteristics, which is the characteristics for the post fault condition, that is when one of the line is now tripped. So, this will keep moving on this, and we will have the accelerating area given by this area A 1, whereas the decelerating area will be given by the area under this curve P e and this line P m. And as we have seen, the maximum value of decelerating area can be obtained up to this point delta max, where delta max we will get equal to pi minus delta 1, that is where this angle we call as delta 1. So, pi minus this angle. So, this is what we will get as the maximum angle, and if we have A 1 is equal to A 2 at some angle which is less than delta max, then system is going to be stable. If it is beyond delta max, then the system becomes unstable. Now, short circuit away from the line ends, that is, now we take a case where the short circuit occurs somewhere in between the two ends, that is in the middle of a line. So, in that case what happens is we have now short circuit occurring in the middle of the line. So, if we look at this diagram, short circuit is occurring in the middle of the line. So, we have two parts of reactances can be divided into two parts, up to the fault point on this side and up to the fault point up to on this side. So, we can now have x 1, this is line 1, and for line 2 we have two parts x a and x b. We have taken the fault on the middle of the line. So, we have the reactance x 2 by 2 and x 2 by 2 on these two sides. Now, that is this is the reference or the ground potential. So, what we have is when this fault, three phase fault occurs on this point, any point P here, which is in the middle of the line, then this part of the reactance is connected to the ground, as well as this part of the reactance is connected to the ground, because this point is now having 0 potential. So, we will see that this is half of the reactance of this line 2, the x 2 by 2 and x 2 by 2 here. So, what we have is x 2 by 2, x 1 and x 2 by 2 here forming a delta circuit, and we can use star delta conversion to convert it into this part of a circuit, that is the star conversion for this delta is x a, x b and x c. We can calculate these values of x a, x b and x c. Then we can further add this x a to x d dash and x b on this side for the reactance of the transformer if we have, and we will have a star circuit which we can further reduce to a delta circuit. So, we have the star circuit here x 1, x a, x b and any reactance on this side that has been combined with that, and x c, and this can again, this star can again be converted into a delta circuit or a pi circuit, where we will have this reactance now, which is the reactance, transfer reactance between two machines, because these two reactances will not be carrying any real power. This voltage is same as the infinite bus voltage, this voltage is same as the generator internal voltage, and this is the reactance between these two voltage points. So, this is the transfer reactance that we get. So, we need to calculate this x 2 in this case. So, what we find is that we have now three curves that we get. First is the pre-fault characteristics, second is the during fault we have now this transfer reactance x 2 coming into picture. So, we will have the P max in this case as E v by x 2 coming into picture, and with this we will have this characteristics coming here, which is the during fault characteristics, and the third one, once the line is tripped by opening the circuit breaker, will be this line. Now, if the fault occurs, what happens is the operating point from this point drops down to this point, that is during fault, this is the characteristics. So, electrical output drops down to this and delta angle keeps on increasing, the electrical power output moves along this line. Now, at delta c, if we clear the fault, it will jump to this point where one of the line is cleared, and it will move along this, and then we will talk about the numerical integration method for solving the swing equation. Thank you.